Today we're learning about complex numbers in polar form. The graph of complex numbers in polar form are going to be done on what appears to be an x and y axis. However, the x-axis is called the real axis, and the y-axis is called the imaginary axis. We know a complex number has a real part and it has an imaginary part. If the real part's 2, you're going to go right 2. If the imaginary part is negative 4i, you're going to go down 4 on the imaginary axis. So right 2 and down 4, that point 2 minus 4i would be plotted in quadrant 4. If we plot the next point, negative 5 is 5 on the real axis to the left. Positive 3i is up 3 on the imaginary axis. So negative 5 plus 3i is in quadrant 2. The absolute value of a complex number a plus bi is defined as the distance between the origin and the point. The definition of the absolute value of a complex number a plus bi is the absolute value of a plus bi equals the square root of a squared plus b squared. A is the real part of the complex number, and the bi is the imaginary part. If you're going to plot the complex number and find its absolute value, you can plot it on your real and imaginary axis. So negative 7 would just go 7 to the left on the real axis. And then we're not going to use the formula or the definition to find the absolute value of negative 7, because you know the absolute value of negative 7 is just positive 7. Absolute value is a distance, and distance is always positive. On the next example, if I were plotting negative 8, 3i, I would go left 8 and up 3 on the imaginary axis, and I would plot that point in quadrant 2. If I want to find the absolute value of negative 8 plus 3i, then I'm going to take the square root of a squared plus b squared. A is the real part of the complex number, or negative 8, and b is the number in front of the I, so that's your imaginary part. If I simplify this, I get the square root of 73. If you can simplify your radical using the factor tree stuff you learned in Algebra 1 and Algebra 2, you may have to do that. Normally, your distances will not be given to you in decimal form. We're going to talk about the polar form of a complex number now. To work effectively with powers and roots, of complex numbers, it is helpful to write the complex numbers written rectangular form in polar form. So we're going to learn some new formulas to do this. We know that a complex number, z equals a plus bi, is written in polar form as z equals r times the cosine of theta plus I times the sine of theta. This formula will be given to you, so you don't have to memorize it. When we're converting between polar and rectangular and polar form of a complex number, you're not going to see x's and y's anymore. You're going to see a's and b's. But the formulas are going to be the same as what we learned on the first day in this section. A is r times the cosine of theta. B is r times the sine of theta. R equals the square root of a squared plus b squared. So that means r squared equals a squared plus b squared. And the tangent of theta equals b over a. So you just have to remember when you're looking at your other formulas that a is the same thing as x and b is the same thing as y. Because we have infinitely many choices for theta, the polar form of a complex number is not unique. Normally, theta is restricted to the interval 0 to 2 pi. This is written and told to you in the reading of the book. It will sometimes be in the directions, but not all the time. You have to remember that. In example 1, we're going to write a complex number in polar form. We need to use our equations to do this. When you're looking at a complex number, a is the real part, and b is the number in front of the imaginary part. So in this particular problem, we need to find r, and we need to find theta. We know r equals the square root of a squared plus b squared, and we know that the tangent of theta equals b over a. So if we plug in our a and b, we get r equals the square root of negative 1 squared is 1, and radical 3 squared is 3. So 1 plus 3 equals 4. The square root of 4 is 2. The tangent of theta is going to be equal to radical 3 over negative 1. Remember, if we were to graph this, we would go left because it's negative 1 on the real axis, and up because it's positive radical 3 on the imaginary axis. So your theta needs to come from quadrant 2. If you think about tangent in quadrant 2, the y value is radical 3 over 2, and the x value is negative 1/2 at 2/3 pi. You need to take this answer and put it back into polar form. And polar form is z equals r times the quantity of the cosine of theta plus I times the sine of theta. And you're done. On the next example, it says to represent the complex number graphically and find the polar form. I always graph, no matter if it tells me to or not. I know that I'm going to the right 4, and then I'm going to go down 4 radical 3. If I type in 4 radical 3 into my calculator, I get 6.9. So I'm going to go down almost 7 tick marks. The bottom line right here is that you understand you're in quadrant 4 when you get theta. So using your formulas again, you know r equals the square root of a squared plus b squared. 4 squared is 16. Negative 4 squared is 16. Radical 3 squared is 3. So you get r to equal the square root of 64, which is 8. And then the tangent of theta equals b, which is negative 4 radical 3 over a, which is 4. And that reduces to negative radical 3 over 1. So in quadrant 4, your y value is negative radical 3 over 2, and the x value is 1/2 at 5/3 pi. So then you take each one of those and you plug it into the polar form, which is z equals r times the quantity of the cosine of theta plus I times the sine of theta. To represent a complex number graphically and find the polar form of the number, you're going to continue doing what we've already done. I always graph it first because I think the graph sometimes provides an insight on the polar form of that number. So if you're only graphing 4i, that means you're only going up to 4 on the imaginary axis. So there's your point. If you think about a polar coordinate plane and you draw in all the circles, then the radius has to be 4. Theta has to be pi over 2 because of the graph. If you actually plugged it into your formula, you know that A is 0 and B is 4. So you'd get the square root of 0 squared plus 4 squared, which is the square root of 16, or 4. The tangent of theta equals B over A. That's undefined. Well, tangent is undefined at pi over 2. So once you get your two values, which again, I prefer to just look at the graph and get, you plug them into your equation. Z equals R times the cosine of theta plus I times the sine of theta. And that's your polar form of a complex number. Same thing on the next one. So these two examples are your special cases. If you were to graph just the number 4, you would only go over 4 units on the real axis. If you think about the radius of that circle again, it's going to be 4. Because if I drew in all of these circles, the radius of the circle is 4. And theta at that spot on the unit circle is 0. Remember, we are told in the first page that theta has to be greater than or equal to 0, but less than 2 pi. So you can't include 2 pi in your answer. That means the polar form of this complex number is z equals r, which is 4, times the cosine of 0 plus I times the sine of 0. Last but not least, we're going to work backwards. We want to represent the complex number graphically and find the rectangular form of the number this time. I think a lot of times it's easier to go ahead and find the rectangular form and then graph. So to find the rectangular form, you're just going to use your unit circle. You're going to leave the 1/4. You're going to go to your unit circle and you're going to find the cosine of 225. It's negative radical 2 over 2 plus I times the sine of 225, which is, again, negative radical 2 over 2. Now you distribute your 1/4 and you get negative radical 2 over 8 plus I, and actually it would be minus I, because it's negative, radical 2 over 8. So there is your polar form converted to rectangular form. So this is polar and this is rectangular. So now if you plot this point, that's your real part, that's your imaginary part. So you go over negative radical 2 over 8, which is teeny tiny, and down radical 2 over 8. So you're going to plot this point in quadrant 3. Having trouble getting this point plotted. There we go. If you want to label some axes, negative radical 2 over 8 is smaller than negative 1/4. So let's do this one more time. You're going to drop the 7 down, go to 0 on your unit circle, and the cosine of 0 is 1. The sine of 0 is 0. 0 times anything is just 0, and 7 times 1 is 7. To graph this, you would go out 1, 2, 3, 4, 5, 6, 7 on the real axis. That's it. Come in and ask questions if you're still confused.